Good morning, DSST 8th graders, and welcome back to week 4. Today's lesson is week 4, lesson 1, writing chemical equations. In today's lesson, we're going to take what we learned last week about physical and chemical changes, as well as how to read a chemical equation, and we're going to take it to the next level, taking how we wrote chemical formulas and now being able to write out full scientific chemical equations this week. First, though, I forgot last week to give the answer to last week's joke. Shout out to Tamir, who was the first student who emailed me the correct answer at a nice and early 8:30 a.m. on Monday morning. Well done, sir. Make sure you're taking care of your sleep, but otherwise, I love your ability to answer science jokes. So, making bad chemistry jokes because all the good ones are gone. Very good. If you didn't laugh at that one, I don't know how to help you. All right, we're going to get started in guided instruction. So this is actually review. I just wanted to review some notes from last week. You do not need to type everything you see on my page. It is okay for you to summarize in your own words the 3 definitions of the 3 parts of a chemical equation. So the 3 parts of the chemical equation are the reactants, the arrow, and the products. And I want to remind us what those represent. So first, the reactants represent what we start with. Everything before the arrow is whatever beginning materials we had. In the video we watched last week, we had a beaker, we poured sugar into it, and then we poured in sulfuric acid. So reactants would be sugar and sulfuric acid. The arrow represents change. What we started with is now changing into something else. And the products are the substance we end up with or are produced. So once again, in our example from our video last week, we started with sugar, we started with sulfuric acid, got mixed together, and then all of a sudden what was produced was this black compound, this smoke and gas coming off of it. Those are the products. That's what we ended up with. Now, I just want to show you 3 examples of chemical equations. Once again, scientists use chemical equations to help communicate clearly with each other what they're talking about. And so my first example is a chemical equation as a model. I have these circles representing one type of element. I have the blue circles representing a different type of element. I can show how they're bonded based upon which ones are stuck together. And then the arrow here in the middle shows it's changing into, and then the box on the right shows that there's a different compound. Now this is what you saw with your Explorer earlier. It is totally fine to represent models using chemical equations. It actually helps us with our visual understanding of what's actually happening at a microscopic level. However, as you've seen and probably gotten frustrated with, drawing models for everything can be really annoying and frustrating. It's not that fast. It's not that efficient. The second example here is writing a chemical equation as a sentence. As you can already see from how much text it took to write the sentence, it's really time intensive and takes a lot of reading to understand exactly what someone's saying. And actually, even after that, it's still confusing. 2 molecules of 2 nitrogen atoms mixed with 6 molecules of 2 hydrogen bonded together change. That becomes way too complicated, and it's not clear enough, and there's way too much room for error. So what scientists use to communicate are these simple chemical equations. We learned 2 weeks ago how to write a chemical formula. And today we're going to be using that to actually write these out as full chemical equations using chemical formulas. So 2N2 plus 6H2 changes into 4NH3. That is short, it's sweet. A scientist can look at that and know exactly what's happening in this chemical equation, and they can exactly know what's happening and whether it's a physical or a chemical change. So from today on, you're going to be learning how to write these chemical equations and read them to understand what they're representing. Let's go ahead and jump to guided practice to see what this looks like in a practice problem. Okay, our first guided practice problem looks similar to things we've done before. Tells us to analyze the chemical equation below, tells us to highlight the reactants yellow and highlight the products in green. So everything before my arrow is what I start with. Those are my reactants. So I'm going to go ahead and highlight those in yellow. And then everything after the arrow are my products. I'm going to go ahead and highlight all of those in green. B, count the number of atoms for each element in the reactants and the products. Okay, so in the reactants, it's asking me how many nitrogen and how many hydrogen atoms we have. Now, this is review. We've already learned how to do this. Just adding one more layer by having us think about the reactants and products separately. So let's start with our reactants. So we highlighted that in yellow. So how many nitrogens do we have? Well, we have N2. So that means I have 2 nitrogens in one of those compounds. but I have 2 molecules of that. So if I think about a visual model, that means there's 2 things stuck together, and then there's a second 2 things stuck together, which means there are 4 total nitrogen. Remember, the other way to do the math here is you take the coefficient, the 2 out front, and you multiply it by how many atoms of each element there are in that compound. So 2 times 2 gives me 4 for my nitrogen. Let's do our second one. How many hydrogens do I have in the reactants? Well, you have 6, and there's 2 hydrogens attached to each other. So 6 times 2 gives us a total of 12 hydrogens in the reactants. Let's go ahead and do the products. Now the products are everything after the arrow. So 4NH3. Now don't get confused here. Remember, we do the coefficient multiplied by everything in the compound. So 4 times 1, remember there's no number there, but that means there's 1 nitrogen. So 4 times 1 is 4 total nitrogen atoms. And hydrogen is 4 times 3, which gives us 12. A very common incorrect answer I get from students is they would have said there are only 3 hydrogens in the products because they forgot that the coefficient needs to be multiplied by everything in that compound. So please don't be the person who makes that mistake. C. Based upon this chemical equation, did a physical or a chemical change occur? Wait, how do I know that? Well, let's take a moment and look. We have to ask ourselves, are there any bonds being broken and new bonds being formed to make a new compound? Remember, if bonds are broken, things are being pulled apart and being rearranged to make new compounds. That is a chemical change. If it's the same compounds, there's no bonds broken, but they're like speeding up because they're getting heated, or they're slowing down because they're being frozen and turned into a solid, that would be an example of a physical change. So let's think about it. Well, we have nitrogen attached to each other and hydrogen attached to each other separately in the reactants, but then in the products, we have 4NH3. So we have 4 of those whole molecules where nitrogens and hydrogens are now attached to each other. That means a new compound must have been made. So this has to be a chemical change because a new compound was formed. Let's move on to question number 2. All right, taking it one step harder. Analyze the chemical equation below. The black circles represent carbon atoms, the white circles represent hydrogen atoms, and the red circles represent oxygen atoms. So write this chemical equation as a chemical formula below. All right, so now instead of writing it out just with the words, we're actually going to write out the chemical formulas. So let's start with our first molecule you see here. I see 1 black circle attached to 4 white circles. So I know my black circles represent carbon, so there's 1 carbon and 4 hydrogens, so that would be CH4, plus, well, what do I have here? I have 2 molecules, and each of these, red represents oxygen, so 2O2. Now, that's everything before the arrow. So then, here's my arrow, change, and then on the right-hand side of my arrow, these are my products. So this first thing is 1 black atom attached to 2 red atoms, so that would be 1 carbon attached to 2 oxygens, so CO2, plus, well, and 1 oxygen attached to 2 hydrogens, so I could say OH2, but we most commonly know that is H2O, and we have 2 of those molecules, so 2H2O. I do want to reiterate something that students have been asking me. They're saying, Mr. Ducharme, does it matter which atom I write first? At this point, no. If you wrote H4C, I would say that's totally correct at this point. Okay? You'll learn as you get further into chemistry why scientists write some elements first and some elements second, and why there's kind of a common formula for how we represent these. But for right now, does not matter the order. Highlight the reactants in yellow and highlight the products in green. Okay, so the reactants, everything before the arrow, I'm going to go ahead and highlight those in yellow and highlight the products in green. Let's highlight those. Boom. All right, now count the number of atoms for each element in the reactants and the products. So in a reactants, here we go. We have 1 carbon as a part of CH4, and I don't see any other carbons in my reactants. So we have 1 carbon. Hydrogens, well, we have 1 molecule, and there's 4 hydrogens in this 1 molecule, so 1 times 4 is 4. And then oxygens, 2O2, so 2 times 2 is 4 oxygens. Now, in our products, we have 1 carbon in this CO2, I don't see any other carbons, so it must just be one carbon. Hydrogens, well, I have 2 H2O, so 2 times H2, well, that's 4. Now, this last one for oxygen is tricky. This is the most common place that students make a mistake when doing this. You have 2 oxygens in CO2, 1 times 2 is 2, but then you also have an oxygen over here in the H2O. So we have 2 in our CO2, but then we also have, well, 2 times 1 gives us 2 more for a grand total of 4 oxygens in our products. Remember, we're not counting just for this one compound. We're counting for all of the products, everything we've highlighted in green. That's the reason why I've been getting you in the habit of highlighting them in green, so you can see everything you're supposed to be looking at one time. Okay, so once again, the reason why there's 4 oxygens is because there's 2 in CO2 and there's 2 in total between the H2Os. You can see that clearly from our model. The red circles all represent oxygens, and everything in our products, there are 4 red circles, so there must be 4 total oxygens in our products. I'm going to simplify this down, so my final answer just says 4. Okay, based upon this chemical equation, did a physical or chemical change occur? Well, this one was a chemical change because new compounds were formed. Remember, that's because I know from my model that the bonds holding those circles together must have been broken to rearrange them and make new compounds. All right. Go ahead and move on to the check for understanding. You're going to pause the video, take your time to complete all of the questions, and then hit play when you're ready to go through the answers. Okay, at this moment, you should be ready to go through the answers for today's check for understanding. Remember, this is the most important way for you to make sure your learning is on track before you do independent practice all by yourself. Number 1, analyze the chemical equation below. White circles represent hydrogen, red circles represent oxygen. Okay, so you should have written the chemical equation as 2H2O in our reactants, and our products are 2H2 plus O2. Highlight everything before the arrow in yellow, like you see on my screen, and then everything after the arrow should be green, like you can also see on my screen. Next, count the number of atoms for each element in the reactants and the products. In our reactants, we have 4 hydrogen and 2 oxygen, and in our products, we have 4 hydrogen and 2 oxygen. I would love for you to make sure you're in the habit of trying to do that from the chemical formula, not by counting the circles. The last one, this is a chemical change because bonds were broken and new bonds were formed to make new compounds. We started with hydrogens and oxygens attached to each other. We ended up with 2 hydrogens attached to each other and 2 oxygens attached to each other. So that definitely is a chemical change. You are ready to move on to independent practice and then take today's mastery check on Agilastic. Best of luck, and I'll see you during the next module.